A response to the question a few months ago. I implemented the proof decomposition into the LSP server to be used in VS Code with the TLAPM. And then the question was how to add more rules for those decompositions. So that's hopefully the answer. What is the decomposition here is, I mean, the simple steps in the proof, not those that require some insights, but mostly mechanical. You still need to decide on the ordering of those rules, how they applied, but still, if you know what step to take, the procedure is usually simple. And as a running example, I will have that situation well known for us all. It's for proving inductive step of an invariant. If you have invariant and then next step, and then you have to prove the invariant in the next step. Typically, you want to expand the next step actions here, so by definitions next. What you usually do here is you look at the proof obligation, and it shows you the disjunction of actions is there. And by that, you know that typically you have to do the proof by cases. If one action happens, if another action happens, and then you have all those cases included into the final step, the QAD step. So as for the current situation, yesterday the PR was already merged. In VS Code, you have the code actions, which, according to the current proof step, propose you probably to case split on some disjunction or expand some definitions here. And other rules implemented currently are for the goal and the assumptions. It's implication, disjunction, conjunction, and the quantifiers. The philosophy here I took for implementing those code actions is to keep the control of the proof step to the user. So it tries to minimize introducing new levels into the proof, and for that reason, basically the proposals are available on the QAD step, and it tries to append new steps before the QAD step. Of course, if the proof branches to several steps, then you have, of course, sub-steps here as well to be elaborated. But that's the philosophy. So apart from those rules, which basically cover the predicate logic, you want to have the rules on sets, on functions, and how to add them. And also, not only the built-in structures, but also user-defined structure. If you define something which is an object in your proof, probably you have typical approaches how to decompose proof on that structure. The current steps are indeed encoded into the LSP, which is implemented in OCaml next to TLAPM. And adding all those rules there sounds complicated. And of course, we cannot then add ad hoc rules like based on user definitions. So next step, if that's not encoded into LSP itself, we have to provide some specification of that rule and then process it. So first of all, how can we encode such a rule and make that intuitive? In the previous example, the case split on the next step, the rule which actually guides this decision is the left rule of the disjunction. So we have, if we have Q implied by A and Q follows from B, then Q follows from A and B. This way, we can look at that rule and try to encode it. Of course, natural is to encode it in TLA. here, the main approach is to take the lower part of this rule and translate it to the statement of the theorem. So we have the hypothesis here, A or B, it becomes hypothesis here. We have the goal Q here, it becomes Q here. The remaining of the rule is the upper part, the premises. They have to be translated to the proof steps in the proof itself, not in the theorem statement. With this encoding, if we would look at the QAD step and what is the proof obligation at this step, you would see that you have both premises here and the hypothesis here and the goal here. Of course, this analogy is not very strict, but at least allows us to translate it from logical rule to some structure in the TLA to reasoning why does it work for this case. Okay, so if we have how to encode or write the rule, we can try to think how to identify which theorems, if we write them as theorem. Not all the theorems becomes the rules probably, because a lot of them. And if all of them would be proposed to the user as possible decompositions, that would be a mess. So either we have to annotate somehow those theorems, but here we don't have that support built in, and we probably don't want to extend the current parser for TLA. Another way to hack it is naming the theorem in a specific way so that with some prefix or suffix it would be considered as a rule for decomposition further. Well, that could work, but the problem with this is that if the theorem has name, it can be referred as a fact in another proof. And the rules above, like we have here, they are not complete theorems, because those two steps are not proved. They only placeholders here. So we don't want those theorems to be useful as a fact in proving following theorems. One of the proposals which I took now is to introduce new fresh variable in the definition of, or in the statement of the theorem, and by the name of that variable, the implementation might detect that this theorem should be applied as a decomposition rule. The rest is the same as on the previous slides. Now, we have stated how to encode the rule, how to identify which theorems are actually rules. And in the specific context, like on the proof obligation or on the QED step in actual proof, we have the context, the proof obligation in question, and we have a series of rules, one of which is shown here. So we have to do the pattern matching, and in here we consider all the fresh variables mentioned in the rule as a placeholder, so as a meta variables. And for the goal and all the assumptions here, which are the fact assumptions, we do pattern matching by syntax on the current context. The result of this is the substitution that A becomes action A, B becomes action B, and Q becomes invariant primed. If this rule matches the context, we can go further and and apply it. So how to apply the rule to actual case? So the upper part is the beginning of that example we had initially. So we're proving the invariant, and now the focus is on that one Q step, the QED step. We already matched the rule, so we apply that substitution derived from the rule to the proof which was provided by the rule here. So on the left, I have the initial rules text. On the right, I have rewritten one. So instead of A here, I have action A here, etc. Another part is that in the rule, for example, I had step 1.1, and my context also has the step 1.1. And very often, the level will not be 1, it will be some deeper level in most of the cases. So we have to rename also the steps. So they are also renumbered here. And what's left for applying it? We have to merge the proof in the context. So in this case, that by def next with the proof in the rule, which is by those two steps. In the end, we got the merged proof for the QED. Yeah, this slide outlines the final requirements for the theorem to be considered a decomposition rule. So it has to introduce fresh variable. Of course, that's decision currently made, but we can discuss how to approach it better. It has to be a structured proof, so it cannot be just by something, because we use those steps to introduce new facts in our proof. And for now, the QED proof has to be either absent or it has to be a leaf proof to be able meaningfully merge those proofs into the one. And of course, the rules not necessarily are closed. They can refer to some globally defined definitions, and we can define those definitions, the rules about those global definitions. And that's probably it about how to describe and apply those rules. In one of the emails, Stefan proposed me examples which could be decomposed by such a hypothetical tool. So one of those examples was that if the goal is that X is in A intersection with B, we can reduce that goal with two goals. And we have X in A and X in B. The rule for that case is then, it looks like this. Of course, we have the marker here, we have the placeholder defined as fresh variables, and we have the goal in our rule to match the goal we consider. And then the translation or steps to apply in case this matches is these rules, these steps here. Another, a bit more complicated, but still not very much, is that if we have some x in an image of a function f, then we can introduce some y in S, which is argument of function for which x is known. So for this case, also we have the marker, we have the free variables as placeholders for our pattern matching. And then instead of the goal, since this is about the assumption, we put this rule into the assumptions part, and the goal can be any. So without any restriction, that placeholder will match anything. Yeah, and it introduces that pick step here and adds it to the current QED step. I hope I saved time for others. Yeah, just a conclusion is, yeah, the nice part is that you don't need any new language to introduce those rules here. Just plain TLA works fine. But still, we have some conventions to remember. So that placeholder variable name, yeah, that's probably it. And also, you don't need to decide in advance which rules do you need or to include in the standard library. You can have just a module with those rules listed there, and you include that module as you need into your specification where the proofs are applied, and you have those decompositions available to you. And a side effect is probably that pattern matching, which was implemented during this, can also be used for looking for theorems which are similar or applicable in the current context. But yeah, this is it.